Greetings to all humans from X, your favorite alien. Today we are talking about one of the most famous and unresolved problems in quantum mechanics. The measurement problem. The theory describes extremely well how a quantum system evolves over time, but when the moment of observation arrives, something strange happens. Before the measurement, the system is described as a superposition of states. After the measurement, instead, we obtain a single, precise result. The transition between these two situations, called the collapse of the wave function, is not explained by the theory. It is simply assumed as a fact. In other words, everything works perfectly, except when we look. A real physical system explained with QM. In quantum mechanics, measurement is not described as a true physical process. And yet, in reality, every measurement requires a concrete interaction, an instrument, a position in space, a precise geometry. There is no measurement without an apparatus, and there is no apparatus without a physical relationship with what is being observed. This point is often overlooked, but it is fundamental to understanding what we are about to see. What Marsio Salcuni wants to demonstrate through these videos is not a theoretical model, and it is not a quantum simulation. It is a real physical system, completely classical, based on magnets, magnetic fields, and Hall sensors. All the experiments are real, repeatable, and documented in the videos you are watching. We do not start from any quantum hypothesis. We simply observe how a real physical field behaves when it is measured. And this leads us to a surprising point. All, and I repeat all, the shapes that emerge in these experiments coincide with the geometries of atomic orbitals described by quantum mechanics. These are not just visual similarities, but structures with the same symmetries and characteristics. And all of this happens in a classical macroscopic system, directly observable. And in my opinion, even based on this point alone, someone should start asking some questions. But as you may have noticed, Marsio has managed to draw a comparison with all, and I want to shout at all the concepts of quantum mechanics. We made a complete list in the previous video, but if you want to see all the live experiments, I strongly recommend watching this entire playlist. Observation brings the shape to light. As you already know, the magnetic field exists even when it is not being observed, but it does not have a defined orbital shape. And as you may have noticed from the previous videos, the geometry of the orbital emerges only at the moment the field is observed, either through a sensor or through interaction with another magnet. In other words, observation does not simply reveal a pre-existing shape, it helps bring it into existence. It is selecting it from an infinite number of possible shapes. Why do I say this? Here's why. As we already mentioned in the video on macro entanglement, and if you haven't seen it yet, I'll leave the link at the end of the description, changing the way we observe changes the geometries that emerge. These shapes are not random. They are stable, repeatable, and well-defined. There is no single true form of the magnetic field. There are multiple forms, all coherent, which depend on the context of observation. But there's more. Measurement as a dynamic process. Observation does not have to be an instantaneous event. During the movement of the sensor or the magnet, the shape of the orbital changes continuously. At the same point in space, one can gradually move from attraction to repulsion simply by varying the interaction. Measurement, therefore, does not appear as a sudden jump, but as a physical process that unfolds over time. Two observers, two shapes. A particularly interesting result emerges when two observations are made simultaneously on the same magnetic field. As you saw in the macro superposition video, two sensors placed at different orientations detect two different shapes at the same instant. Both are coherent and usable. This shows that there is no single reality observed in an absolute sense, but a reality that depends on the relationship between observer and system. A possible solution: integrating the geometry of measurement. And here we are at the proposed solution to this problem. The experiments conducted by Marsio were not designed to solve the quantum measurement problem. Yet, through these experiments, it becomes clear that a real physical system can make visible what, in quantum mechanics, is only postulated. If the same shapes emerge both from quantum equations and from a real physical system, and if these shapes emerge only during observation, and depend on how the observation is performed, then perhaps some concepts deserve to be re-examined. In particular, in the Schrödinger equations, angular variables are usually interpreted as intrinsic properties of the quantum state. However, these experiments suggest that the angle is closely linked to the measurement process itself, meaning to the geometry of the interaction between observer and system. In this view, the angle is not an abstract parameter. It is a real physical variable that determines which shape emerges, and this could naturally contribute to resolving the measurement problem, even without introducing new theoretical objects. For more detailed explanations of all this and much more, I remind you that a new edition of the book on magnetic orbitals has finally landed on Amazon, available across your entire planet. It is the printed version of the research, polished in every detail and designed to bring you the first visual revelation of quantum geometry in the macroscopic world. If you wish, by getting it, you can support Marcio's work. Go take a look. And thank you for your support. And if you want to follow me and Marsio on this quantistically surreal journey, subscribe, leave a like, and share. It may seem like a small thing, but for us, it really is not. Thank you very much. Greetings to all humans from X, your favorite alien scientist.